Hello there, ladies and gentlemen. So today we're going to be talking about electrochemistry, which is electricity and chemistry kind of merged together, if you will. Before we really delve into some of the terms that are sitting there in your notes, we're going to discuss some basic ideas. Here is a pretty common demonstration that is done. Someone has placed a piece of silver into a test tube, and the test tube is filled with copper sulfate, and then into the other test tube they've placed a piece of copper, but that test tube is filled with silver nitrate. So again, the solutions are copper sulfate and silver nitrate. The metals are silver and copper. So they're really testing silver against copper, and they're testing copper against silver. This silver is a piece of metal, so it is a solid. This copper is also a solid. And obviously these copper ions are dissolved, so these are copper plus 2s, and these are silver plus 1s in the solution. And so when we put these metals down into the solutions, a battle over electrons occurs. And whichever element is, you could actually look at it two ways. Whichever element is better at taking electrons, gaining electrons, will gain them. Or you could look at it the reverse direction. Which element is better at giving away the electrons? So they get both put into the solution, and then you sit and watch. If silver is better at taking, then these silver atoms, or ions I should say, these silver ions will take electrons off the copper, and they will become copper plus 2s. If the copper ions are stronger, they will take electrons off of the silver, and the silver will go into the solution. So this is a pretty common demonstration. So the question is the copper or silver better at gaining electrons? And then, since this is all about electricity, like, how do we use this to create batteries and to talk about electricity and things like that? So what it turns out is that if you put, this is copper, if you put the copper into the silver, and the copper wire is in a silver nitrate solution here, what we slowly see happen is this is a giant pile of silver that is now solid, that is coming out of the solution. So the solution had silver in it, and now it does not. So the copper, and we can also see, remember the copper solution, this solution was clear. Silver nitrate solution was clear. And you can see it's going from clear to very blue. Very blue. So we have evidence that the copper is going into the solution, and we have evidence that the silver is coming out of solution. The evidence that it's copper's going into solution is the solution is now blue. And look at this. The copper sulfate solution was blue. Copper ions, when they're plus 2, tend to be a blue color. And the silver is very obviously piling up here around that spiral they put in. So the copper metal will react with the silver nitrate. Interesting. So let's look at what this means. What does this mean? Silver does not react in the copper sulfate. Let me zoom out just a bit. I think I zoomed in too far for you. That silver sits in there, and it's not going to react because silver is better at gaining electrons. Well, the silver already has its 2 electrons. It's not going to gain any more from the copper that has lost its 2 valence electrons. But the other one, though, yeah, the copper will lose electrons, and then it will dissolve into the solution. So the silver ions that were in this solution end up gaining the electrons and then precipitating out as this kind of like solid that we see here. It looks kind of like a weird looking cloud, but it's actually a solid. If copper is losing electrons, losing electrons means it's been oxidized. And then the silver is gaining electrons. Some of you were like, oh my gosh, that is from way back when. One of the reasons I love this chapter, Leo Gurr, we love this chapter at the end because it actually forces us to review a lot of the different things we have learned. Lose electrons, oxidation, gain electrons means reduction is occurring. This is way back when we did the redox chapter. If you need to go back and review redox, I suggest you do. We'll talk about balancing redox reactions again a little bit. I can almost hear you groan back here in the past where I am recording this video. All right, back to the future now. So, what's occurring reaction-wise? Oops, that's the wrong pin. Ignore this thing over here for a second. Oh no, I typed the wrong thing. Just a second. Alright, that probably seemed like just a second to you, but it took some time. So, what happened in here and in here? This copper was a metal, and now it's an ion. So we had silver was in the solution, silver nitrate, silver ions. Copper was a piece of metal. Let's write some states of matter on here. State of matter for copper, solid. Silver was aqueous. Silver has a +1 charge. Afterwards, the copper has dissolved in. It's a light blue. It's now aqueous, and the silver is now a solid. So 2 electrons are being exchanged. If the copper is becoming copper +2, it is losing 2 electrons. The silver can only gain 1 electron, so there must be 2 silvers. So it's balanced via old redox methods. This is a simple redox. You didn't have to do all the waters and hydrogens and everything like we did in the past. So how in the heck am I going to figure out which metal is better at taking electrons? Well, you're going to be given a list. You have to look through the list and look at values, and the list is from strongest to weakest. And you have to be able to recognize which side is strongest on the list, which side is weakest on the list. Shockingly, fluorine will be one of the strongest at taking electrons, and your non-metals, your metals on the opposite side will be the best at giving them away. But we're going to look at that list in a minute. Primarily, now keep in mind, copper losing electrons to silver. We are not going to be focused on this type of reaction much, not putting a metal into a solution of its opposite. We are instead going to be focused on simple galvanic batteries, and I'll explain what galvanic means in a couple minutes. So here is, can't quite see that. So we have a solution. This is a blue solution of copper sulfate. I'm going to add blue so that you know it's copper sulfate. And then in the other one, the silver nitrate didn't have a color, but I'm just picking gray to pretend it was really colorless. Okay, so we have 2 solutions. We have a piece of metal stuck. Notice this is copper in copper sulfate. This is copper in copper sulfate. And then over here we have silver in silver nitrate. And then they are connected with something we like to call a wire. What? What's a wire? A piece of metal that's connecting this metal to that metal. And then they are also connected with a clear glass tube that's called a salt bridge. And salt bridge have ions floating in them, and we will get into that in a minute. But really what I want to explain here is that the same reaction we just talked about, silver gaining electrons from copper, is going to occur right here. But if you notice, this copper is not touching the silver ions. Those silver ions are in here. And yet the copper is over here. So the copper, let's scroll back. What's copper going to do? It has no charge. It's going to become +2. It's going to lose electrons. The silver is +1, and it's going to go to 0. It's going to gain electrons. So right here, we're going to have silver gaining electrons, and over here we're going to have copper losing electrons, and those electrons are going to go through the wire and be gobbled up on the opposite side in this other beaker by the silver that's floating around in it. The silver that's floating around in here gains those electrons, and then this gets a new silver atom on it that has no charge. If copper atoms here are losing electrons, then those copper atoms must be going in, and we're gaining copper ions here, losing copper atoms. These copper atoms are given up 2 electrons. Those electrons go through the wire, get pulled through the metal and into the solution. And that is how a galvanic cell works. And this is what we're going to talk about over and over and over again for the next couple minutes. Is that you can put 2 metals in solutions kind of themselves, right? Silver, silver solution, copper, copper solution. Connect them with a wire, connect them with some sort of ion salt bridge, and then electricity or electrons will flow through the wire from the weaker element to the stronger element. The stronger at gaining electrons. So the silver ions are better at gaining electrons. So now, let's actually go to the notes. There's lots of terms for the things we just talked about. So, what are some of the terms? These things we're discussing here are called galvanic cells. This is a very similar battery to the one I was just showing you. It's a zinc and copper battery. We'll get into that in a minute. A galvanic cell, the chemical energy or pull is converted into electrical energy as the electrons flow, and then we take advantage of that flow. As the electrons flow through, we put light bulbs in the way, and well, that's a beautiful light bulb. And the electricity flows through the light bulb, and we put it to work, or something like that. That needs to go away. All right, there we go. So what else could we have? There's different terms. There's the cathode. There's the anode. There's the salt bridge. There's the electromotive force. We'll get to that in a second. Cathode and the anode are terms you may have heard before. So the cathode is where we're gaining electrons. The anode is where we're losing electrons. So whichever element is losing electrons and is being oxidized, that's at the anode side. Whichever side is gaining electrons, that's the cathode. So one of the goofy little phrases you hear is you might hear a Leo cat gers, like Leo the lion or some sort of cat named Leo. A Leo, this is our Leo ger, just expanded out so that it includes anode and it includes cathode in there. So the anode side is wherever the electrons are being lost. Here the zinc is got electrons leaving it, so this is the anode. Here the electrons are coming to it. This is the cathode. If you actually look at a battery, the cathode is labeled with a positive sign. The anode is labeled with a negative sign, because the electrons leave the anode and then arrive at the cathode. Warning! Physicists do this backwards on purpose. Physicists don't like the electron moving around. They know it's moving around, but they don't like to deal with negative values. So the next 30 seconds is really about physics and not about chemistry. Okay? In chemistry, we say the electrons are flowing from the anode to the cathode. In physics, you will say the opposite. You will pretend that a positive charge is flowing that way. That a positive charge is leaving the cathode and going to the anode. And there isn't really a positive charge flowing through there. They understand that this is just some sort of idea or convention they came up with, but they like dealing with positive values more than negative values. So if the negative's going one way, physicists say then the positive must be going the other way, and they call this conventional current. We don't teach or deal with conventional current in chemistry, so I erase that from the board. So anode is where the oxidation occurs. Cathode's where the oxidation occurs. Anode is where the, dang it, I keep saying backwards. Cathode's where the reduction occurs. Anode's where the oxidation occurs. I don't think that this term is in there, but if it is, please cross out the word oxidizing agent or reducing agent. I just done it in purple. I think I deleted it from the actual notes, but I didn't delete it from my flip chart. So it's just that these agents were eliminated vocab-wise a couple years back. They're perfectly good, but sometimes people get them backwards. So they've just been removed from the College Board's vocabulary. Salt bridge allows the ions to keep the charge balanced. If we had electrons going over here, we would slowly have a buildup of more and more and more and more and more negative charge. And that charge would actually end up negating the pull of the one element that's stronger over the other one. And so to get around this, we allow ions to flow through a salt bridge. Now these ions are not the same. The positive ion is not one of the ones we have in common. This is a sodium ion, zinc, copper. So the sodium ions are allowed to flow. Since the negatives are flowing into here, the electrons are flowing into here, you might have sodiums being drawn in. Or you could think of the nitrates, which have a -1 charge, as flowing in. So there's kind of a loop here. Electrons are going this way. And then the negative nitrates. And it's a loop. Now the nitrates are not going up the metal. I'm saying the charge is going up the metal. The negative charge of the electrons or the negative charge of the nitrates. All right, so you got a loop. That's a complete loop. It's a closed circuit, not an open circuit. It's closed because the switch is down, connecting the wire. And there's a potential for electrons to flow from one side to the other, which we call voltage, and we will talk about that in a minute also. Salt bridge, check. Electromotive force, or EMF. EMF, this is the pull of the protons in the nucleus of one metal on electrons. And the copper ions down here are strong enough to pull the electrons through the wire. So what's happening is kind of at the surface, coppers are taking electrons from coppers, which are taking electrons from the wire, which are taking electrons from the wire, which are taking electrons from the wire, which are taking electrons from the zinc. And when they take them from the zincs go into solution. It's kind of a domino effect. On the other side, there's also a tug of war. So both sides have a tug of war going on, but this side has a bigger tug than the other side. So the electrons are flowing this way towards the copper. So the electromotive force is really about which atom has a greater pull on the electrons, which nucleus has a greater pull on the electrons. Why is a little bit more difficult to explain as to which one's which. It would probably go into, I don't know, shielding effect. It might go into effective nuclear charge. There could be a lot of things going into it. You'll be glad to hear we're not going to get into those things. And then voltage. Voltage is what we call the measurement of difference between the two. It is kind of a weird unit. It's joules, which is energy, and coulombs, which is charge. We're going to get more into charge a little bit. Coulomb is a measurement of charge and what's the charge of electrons and things like that. In the construction of a galvanic cell, keep in mind the direction of electron flow. You have to keep in mind which element is stronger than the other, and we're going to look at some data in a couple minutes to figure out which one is stronger. So this is the essence of batteries. One element is stronger than the other element. It's in a solution of itself, and then you connect them with wires and a salt bridge, and the electrons can be pulled through. And here ends the first video on electrochemistry.